is polar or nonpolar. Basically, we're trying to decide if the electrons are going to move to one side of the molecule or not. So what we're going to be looking for is if it's symmetrical or non-symmetrical. So basically, if your molecule is symmetrical, then it's probably going to be nonpolar. And if it's something like a tetrahedral and all the groups match with 4 identical groups, it's going to be nonpolar. So like CH4 has 4 electron domains, and it's very symmetrical. It is going to be nonpolar. And then anything that is non-symmetrical, so there's other things that are, so like, we'll look at some more. If it's non-symmetrical, then it's probably going to be polar. So those are the things that we're going to look for. So let's go back here. The first thing that we can do is look at the Lewis structure to help us decide if it's polar or polar or nonpolar, if it's symmetrical. So we got CO2. So we need to know how many valence electrons. We're drawing the Lewis structure. How many valence electrons are in carbon? 4. And how many are in oxygen? There's 6. But we have 2 oxygens. So that gives us 12. So in our structure, for CO2, we're going to have a total of 16 valence electrons. I'm going to put carbon in the middle because it's carbon. Also, there's only one of them. And I'm going to connect the oxygens. So we've used 2 4 electrons. We've got 12 left. I'm going to start by sticking them around the oxygens. So I've now filled the octet of oxygen. We've got 2 4 6, 2 4 6. So that's we've used 12 more electrons. And now oxygen has an octet, but carbon doesn't, so we're going to move electrons from oxygen in between carbon and oxygen. So now we have a double bond between the carbon and the oxygen. And we have an octet around carbon now. So we've got 2 4 6 8. Around oxygen, we've got 2 4 6 8. So both of these atoms have an octet. Okay, and then we have to decide, is this a symmetrical molecule or a non-symmetrical molecule? So this one is very symmetrical. So it's linear so we need the molecular geometry. And because we only have 2 electron dense areas around the central atom, then the furthest those electron groups can be away from each other is linear. Or we can use our chart. So 2 electron dense areas gives us a linear geometry. So that's how I know that this is symmetrical. So then we do have polar bonds here. The electrons are going to be trying to get to oxygen. Oxygen is more electronegative. We can always use the ALEX periodic table to look at that. So oxygen has an electronegativity of 3.4. Carbon has an electronegativity of 2.6. So the electrons are going to move towards oxygen. So yes, we do have polar bonds, but because those polar bonds are symmetrically pulling against each other, they're going to cancel out, and this is going to end up being a nonpolar molecule because it's very symmetrical. This is something that, if this is tricky for you, I would probably put a few of these examples on my note card so that you have some examples to reference on the test. So this one's nonpolar. Okay, the next one is Cl2. So Cl is over here. It has a 7 valence electrons each. So I'm going to just quick draw this. This one, we need to draw the Lewis structure or have an idea of what it looks like so that when we we need to decide if it's symmetrical or not. Okay, so this one, Basically, anytime you have like O2, Br2, H2, these are all going to be nonpolar because they're pulling equally. They're identical atoms, and there's not an imbalance of electronegativity. These are going to share equally. So remember, polar bonds is when they're sharing unequally. So if they're identical, they're sharing equally, they're going to be nonpolar. So anytime we have an unbalance and something that's not symmetrical, unsymmetrical, that's going to be polar. So this is going to be nonpolar again. And again, this one might be a good one to have as an example on your note card. Okay, the next one is NH3. That is ammonia. So let's quick draw that one. Let's see. So we've got NH3. And we need the number of valence electrons. Nitrogen is in this column. It has 5. Hydrogen is over here. It has 1 each. So nitrogen has 5. Hydrogen, there's 3 of them. Each has 1. So overall, we have 8 valence electrons we need to show in our structure. So we're going to start by taking nitrogen, connecting the hydrogens. Doesn't matter too much where we put them. So I've got 2, 4, 6. Use 6. We have 2 left. Looks like dividing. We're going to put them on the nitrogen to fill the nitrogen's octet. Okay, so we have something that has a trigonal pyramidal geometry. And I know that because I have 4 electron dense areas and 1 is a lone pair. So if I go to my electron geometry chart, we have 4 electron dense areas. 1 is a lone pair. When I'm talking about polar molecules, I need to know the molecular geometry. So this is trigonal pyramidal. So we kind of have this point. Our molecule has one side that has a lone pair and one side that doesn't have a lone pair. So this is starting to look unsymmetrical. If we have all the same groups in like tetrahedral, this is going to be nonpolar because this one's very symmetrical. There's not one side of the molecule. This starts being unsymmetrical. This is going to be polar. So let's go back to our... Oh, the other thing we can look at is in Alex, we can look at the electronegativities. So we have hydrogen, which is 2.2, nitrogen, which is 3. The electrons are going to move towards the bigger number. So electrons are going to be moving towards the nitrogen. So if we kind of imagine what's going on, these are going to go towards the nitrogen, these are going to the nitrogen. And then if you remember the shape, we kind of have a pyramid. This is kind of like the bottom, and then the top of our pyramid has a lone pair. So our electrons are all going towards the nitrogen. So this is not symmetric. Not symmetric. And so it's going to be polar. If it's non-symmetric, it's going to be polar. So we'll go in here. We'll choose polar. And our electrons are going to move towards our nitrogen. Okay, let's do one more example of predicting if a molecule is polar or nonpolar. So this one has some more interesting molecules. So we have H2S. So the first thing that we need to do is draw the Lewis structure and then decide if it's polar or nonpolar based on its molecular geometry. So we need to know what it looks like before we can decide if it's polar or nonpolar. So we have H2S. We need to figure out how many total valence electrons to show. So let's go back to Alex. Let's look at our periodic table. You will get this on the test. So hydrogen is in this first column. It has 1 valence electron. There's 2 of them. So hydrogen brings us 1 each, and there's 2. And then sulfur is over here in the 6A column. That gives us 6 valence electrons. So then we add those up. this structure should have 8 total valence electrons. Something that you can notice is if you're looking here, we have oxygen is right above sulfur. Oxygen also has 6 valence electrons. So the Lewis structure of H2S is going to look pretty much the same as H2O. So if you can start identifying these patterns, that can also help you on the test. If you put H2S as an example on your note card, it also will go for H2O or H2Se because they all have the same number of valence electrons. Okay, let's go ahead and start drawing this. So we're going to put sulfur in the middle because there's one of them. And then we're going to put our hydrogens. It doesn't really matter where they go. We've used 2 4 electrons here. We have 4 electrons left. We're going to put these around our central atom because our outer atoms are full. Usually we fill up our outer atoms with these extra electrons, but hydrogen only wants 1 bond, so it's full. So we're going to put these around sulfur. 1, 2, 3, 4. So now we need to look at the molecular geometry. So we're going to look at the central atom. Well, let's show that we've used all of our electrons. This central atom, how many electron dense areas does it have? So we have a lone pair, we have a lone pair, and then we have a bond and a bond. So we have 4 electron domains or electron groups, and then we have 2 lone pairs. So we need to use our electron geometry chart to figure out the shape. Okay, so this one is more interesting than some of them. So if we have something that is, we have 4 electron areas. So the electron geometry would be tetrahedral. But we don't just have bonds, we have lone pairs. So we have 2 lone pairs in a tetrahedral electron geometry, so our molecular geometry is bent. So when we're looking at this, what's happening is our hydrogens are really pointing one direction, and our lone pairs are pointing one direction, and our electrons are going to move up towards the lone pair. So basically, if we look at this molecule, this is unsymmetrical. So this is something that we have to kind of think in 3D space. So if we really were looking at this, our hydrogens would point one way. So maybe like this, our hydrogens, one would be pointing up forward and one would be pointing back. One would be pointing up, and then our lone pairs, we have a lone pair and a lone pair. So when we're looking at this molecule in 3D space, our electrons are all going to be going up towards the oxygen, up towards the lone pairs. So this is unsymmetrical. We have one side that is positive and one side that's negative. And so this is going to be polar. So anytime we have something that's unsymmetrical, that's going to be polar. So anytime we have something that is bent, if it is bent, that means it is polar. So watch out for that, especially on the test. That might be something that I would put on my note card to help me remember. This will come up on the test, so be ready for that. So this is going to be polar, and the atom that's closest to the negative side is, if we look at the electronegativity, we're looking for the one that has bigger electronegativity. So sulfur is 2.6, hydrogen is 2.2. Our electrons are going to be moving towards a bigger electronegativity, which is sulfur in this molecule. Okay. The next one is O2, the O2 molecule. So the first thing that we need to do is draw the Lewis structure for oxygen, the oxygen molecule. So oxygen, we just looked, it has 6 valence electrons, and there's 2 of them. So that gives us a total of 12 valence electrons that we need to show in our structure. We have 2 oxygens together, so I'm going to first draw a bond together. That uses up 2 electrons. We have 10 left to use. I'm going to start by putting them around our oxygen. So 2, 4, 6, 8, 10. We've used up all 10 electrons. This oxygen doesn't have enough valence electrons around it. It only has 2, 4, 6. So we're going to make this oxygen share a pair of lone pairs, a pair of electrons with the other oxygen. So then if we draw this, this lone pair is going to move between the oxygens and act as a bond. It doesn't really matter which one we pick. And now this oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. Remember, if they're in a bond, both atoms can see them. So 2, 4, 6, 8. Both of these have an octet, so we're good. And now we need to look at the shape. So anytime we just have two atoms, if we just have two atoms, this is going to be linear. And this is a specific case where if we have two atoms that are identical, they're going to be pulling equally. If you have two atoms pulling equally, that's going to be nonpolar. Okay, so that's something that you could put on your note card if you need. Anytime you have two identical atoms in a bond, that's all you have. That's going to be nonpolar. And then we don't have to pick a side. All right, the next one is CH3Cl. So the first thing that we always need to do with the Lewis structure is we need to figure out how many valence electrons for each atom. So we have carbon, hydrogen, and chlorine, and we have 3 hydrogens. If you start kind of memorizing these, then you don't have to do this every time, but until you get really comfortable with knowing how many valence electrons and what the structures look like, I would do this every time. I know it's a little bit tedious. So we've got carbon. Carbon has 4 valence electrons that's in this column, so 4. I'm going to write that down. Hydrogen is over here. It's in this column. It has 1 valence electron, but there's 3 hydrogens in this molecule. And then chlorine is over here. It's in the 7A column, so it has 7 valence electrons. So I'm going to go ahead and add those up. So we've got 7 plus 3 is 10, plus 4 is 14. We have a total of 14 valence electrons that we need to show. Oops. So what we're going to do, we have to decide, we have this molecule, CH3Cl. We have to decide which is going to be in the middle. So if we have carbon, that's probably the best bet. If we only have one carbon, that's probably going to be the best bet to put in the middle. So let's go ahead and do that. We're going to put the other things around the carbon. So we've got 3 hydrogens. It doesn't really matter where they go. And then we have a chlorine. Okay, so we've used 2, 4, 6, 8. Remember, 2 electrons per bond. So you've used up 8 electrons. I'm going to subtract those off. We've got 6 electrons left. Remember, hydrogen only wants a bond, and so then its valence shell is satisfied. So with 2 electrons. So this one's satisfied. This one's good. This one's good. So we're going to fill out this chlorine. This chlorine has 1 bond, but it needs 8 electrons. So we're going to give these 6 to this chlorine. So 2, 4, 6. We've used all of the valence electrons in our diagram. Now chlorine has 2, 4, 6, 8. Hydrogen has 2. Hydrogen has 2. Hydrogen has 2. This carbon has 2, 4, 6, 8 electrons in its structure. So now we know what the Lewis structure looks like. So now we're going to count electron groups around the central atom. So we're going to look at carbon. Carbon has 1, 2, 3, 4. 4 electron groups around the central atom. None of them are lone pairs. So if we go to this chart, molecular geometry chart, we have 4 electron groups. It's tetrahedral. So we have to, the reason we're doing this is we need to look at what it looks like in 3D space. So tetrahedral, we have 2 going one way, 1 kind of going up, and 1 going kind of down. So just imagine these electron groups are trying to get as far away from each other as they can. And so some of them are kind of pointing up and down and away. So if we have 4 identical groups in tetrahedral, then that's going to be nonpolar. As soon as we add a new group, that's going to be polar. So let's go back to our structure. We have 1, 2, 3. We have 3 identical groups and a different group. So this is going to be polar because it's going to be unsymmetrical. Our electrons are going to move towards this chlorine because chlorine has a greater electronegativity. So we can kind of imagine this as like we have kind of like a pyramid sort of, and then our chlorine is pointing up. So our carbon is in the middle. We have these hydrogens. Okay. And so because it's unsymmetrical, we have one side that looks different. That's going to be polar. Okay, if we had 4 identical groups, so imagine they were all hydrogens or all fluorines or all chlorines. I'll try to make this one pointing down more. If we had all of the same groups, this is going to be nonpolar. So something like CH4 would be nonpolar, or CF4 would be nonpolar. Okay, but as soon as we add one or more different groups, that's going to be polar. So something like CH2Cl2, that's going to be polar. We're going to have one side of the molecule that has chlorines, like this, and one side that has hydrogens. Our electrons are going to move towards the chlorines. So let's finish our Alex topic. So this one's going to be polar. It's unsymmetrical. The atom closest to the negative side is going to be chlorine. The other thing we can do is we can look at the electronegativity of hydrogen, which is 2.2. Chlorine is 3.2. Our electrons are going to move towards the larger number, the bigger electronegativity.